Imagine a self-driving car approaching a stop sign. To a human driver, the sign is obvious. But if an attacker makes a few imperceptible changes to the pixels on that sign, the car's computer vision system might classify it as a speed limit sign. The car accelerates right through the intersection. This vulnerability is exactly why neural networks, despite their massive leaps in accuracy, remain a liability in safety-critical environments like autonomous driving and automated malware detection. Security researchers model this scenario as a white box targeted attack. The adversary has complete access to the neural network's architecture and weights, and they use that mathematical access to force the system to output a specific, incorrect label. Until we can reliably defend against these adversarial examples, deep learning models cannot be inherently trusted in environments where errors have physical consequences. For a brief moment, the machine learning community thought they had a solution. A technique called defensive distillation was proposed, and early tests showed it dropping the success rate of adversarial attacks from 95% down to 0.5%. Then, researchers Nicholas Carlini and David Wagner published a paper specifically challenging the mathematical foundations of that security claim. Their thesis was direct. Defensive distillation offers almost zero actual security. The previous attacks only failed because they were poorly formulated for this specific defense. To prove it, Carlini and Wagner developed 3 new attack algorithms and achieved a 100% success rate against defensively distilled networks. Every single image they targeted was successfully misclassified. These results suggested that the perceived drop in attack success wasn't due to a more robust model, but rather a set of common attack formulas that were failing to adapt to the new architecture. To understand how they broke this defense, we have to look at the 2 final layers of a classification network. First, the logits, which are the raw, unnormalized scores the network assigns to each possible class. Second, the softmax layer, which converts those raw scores into a final probability distribution. An attacker targets these layers by tweaking image pixels, but to be a true adversarial attack, the changes must remain visually imperceptible. This boundary is strictly measured by distance metrics known as LP norms. Carlini and Wagner built attacks for 3 distinct paths. The L0 metric is a strict count of how many total pixels have been altered, regardless of how drastically you change their individual intensity. The L2 metric measures the overall Euclidean distance between the original and the modified image. This allows an attacker to make thousands of microscopic changes distributed across the entire image. Finally, the L-infinity metric places a limit on the maximum change allowed to any single pixel, with no limit on how many pixels you modify. A successful attack must manipulate the raw logits enough to change the classification while remaining mathematically invisible within these rigid limits. This brings us to defensive distillation. The defense starts by training a teacher network on a dataset. Instead of using strict categories like 7 or 1, the teacher evaluates the images and outputs soft labels, hidden class probabilities that might say an image has an 80% chance of being a 7 and a 20% chance of being a 1. To make these soft labels even smoother, researchers introduced a temperature constant, labeled T, into the softmax function. By dividing the logits by a high temperature value during training, the probability graph flattens. The network is forced to learn a smoother, less confident distribution. Next, a second network, the distilled network, is trained. But instead of the original raw data, it is trained to mimic the teacher network by consuming those smoothed-out soft labels while still maintaining that high temperature constant. Once training is complete and the distilled network is deployed for real-world use, the temperature constant is set back to 1. The strategic intent here is to remove mathematical blind spots. By forcing the network to train on smooth probabilities, the defenders aim to iron out the sharp nonlinearities where adversarial examples were thought to live. But Carlini and Wagner discovered a flaw in the implementation. When you train a network at a temperature of 100 and then test it at a temperature of 1, the raw logit values scale up by a factor of 100. When these massive logit values hit the normal softmax function, the resulting probability becomes an extreme decimal.
It pushes the limits of standard 32-bit floating-point math, and the computer rounds these values to absolute 0 or absolute 1. When probabilities snap to 0 or 1, the mathematical gradients entirely vanish. They go flat. Optimization algorithms need these gradients to know which direction to adjust the pixels to reach an adversarial goal. Prior attacks, like fast gradient sign, relied exclusively on a measurement called cross-entropy loss. When those algorithms tried to calculate that loss on a distilled network, they hit these zeroed-out gradients. With no data to guide them, the attacks failed. Distillation didn't actually remove the model's vulnerabilities, it merely hid the gradients, rendering previous attack formulas numerically blind. To prove the vulnerabilities were still there, Carlini and Wagner abandoned the standard loss functions. They reformulated adversarial generation as a rigorous optimization problem. They designed a new objective function called F6.
This equation completely bypasses the final softmax layer. Instead, it looks exclusively at the raw z-values, the logits, and isolates the target class score from the maximum score of all other classes. By targeting the raw logits before they get crushed by rounding errors, the gradient signal is restored. The mathematical landscape comes back into focus, allowing the optimizer to see exactly how to modify the image. They still face the challenge of box constraints. If an optimizer blindly changes pixels, it might try to assign colors outside the valid range of 0 to 1, creating a mathematically impossible file. Standard clipping methods often stall the optimizer. Carlini and Wagner solved this by using a change of variables method with a hyperbolic tangent function. This natively forces all modifications to stay within valid image boundaries without stopping the search. By treating adversarial generation as an unconstrained optimization problem, the researchers were able to quantify and expose the network's inherent vulnerabilities. The efficacy of these new attacks was proved on MNIST handwritten digits, CFAR10 images, and inception models on ImageNet. This grid shows the original source images next to successful L2, L-infinity, and L0 adversarial counterparts. Against both unsecured and distilled networks, the algorithms achieved a 100% success rate. Looking at this L2 grid for MNIST, we can see the precision of the method. Every digit in the left column is successfully manipulated into the target digit listed at the top, with almost no visual distortion. The L-infinity results are just as stark. By limiting the maximum allowable change to any individual pixel, the attack remains completely invisible to the human eye, even while the computer is entirely fooled. On the high-resolution ImageNet dataset, the attack was so precise that it could change a classification by flipping only the lowest order bit of each pixel. The visual evidence proves that human perception is an unreliable judge of model security. If the pixels are shifted optimally, the machine's internal logic is compromised without a single visible artifact. Carlini and Wagner also proved that distillation fails, even if its gradient masking is technically perfect. They utilized transferability, the property where an adversarial example optimized for one model successfully tricks a completely different, unrelated model. By increasing a parameter called kappa, researchers created high-confidence adversarial examples on an unsecured proxy model. This forced the proxy to be extremely certain about the incorrect label. When these high-confidence images were fed into the distilled network, they successfully transferred the error. This bypass is total. An attacker doesn't even need to calculate the target's hidden gradients. They just build their weapon on a proxy and fire it at the protected system. Any defense that relies solely on gradient masking is fundamentally broken. While this research focused on image classification and LP distance metrics, its implications for AI security are much broader. The paper proved that causing an algorithm to fail through floating-point rounding errors is a false metric for security. It's a numerical shadow, not structural resilience. The standard for evaluation has changed. True robustness can only be measured by a defense's ability to withstand strong, adaptive optimization attacks. Defensive distillation failed because it attempted to hide vulnerabilities rather than fix them. True neural network security requires models that are resilient in their very structure, not just in their mathematical representation.